Fermi Golden rule. Fermi Golden rule is a formula that describes the probability of transition per unit time from one energy eigenstate of a system into other energy eigenstates in a continuum because of perturbation. Say there is one energy eigenstate of a system. These are all different eigenstates which are developing a continuum. See, in between E and E plus D, more and more eigenstates are present, but these eigenstates are almost having the same energy. Therefore, the transition from one eigenstate to any one of the eigenstates present in the continuum is described by our Fermi Golden rule. To understand this definition, we should think about semiconducting material. In the case of semiconducting material, say the conduction band is having different energy levels. Valence band is also having different energy levels. In between valence band and conduction band, a forbidden gap of width 2 mc square is present, in which no energy level can exist. If you think about an electron in the positive energy and the negative energy state, say here is an electron is present in this state. If this electron wants to make a transformation from valence band to conduction band, which is not allowed because of forbidden gap of width 2 mc square. However, an amount of energy greater than this 2 mc square is supplied to that electron. That electron will make a quantum jump to any one of the energy state existing in the continuum, the conduction band. See here, the energy supplied to the electron is called perturbation. As a result of perturbation, that electron will make a transformation to the conduction band. So the conduction band is carrying so many energy levels. This electron will make a quantum jump to any one of the eigenstates existing in the continuum. Then such a transformation is explained with the help of our Fermi Golden rule. The transition probability per unit time is T equal to 2 pi by h cross, then absolute square of the matrix element into rho of m, density of final state. Here the density of state means the available states for the occupation of the particle in the continuum of state is called density of state. Considering a continuum of states, the energy levels are almost the same. Here the energy levels are almost the same. The continuum has different states lying between the energy E and E plus DE. See, in between E and E plus DE, more and more eigenstates are present. A rho m is the density of final states. Therefore, rho m into DE is the number of such states in the energy range E and E plus DE. Rho m into DE is the number of available states. According to time dependent perturbation theory, the transition probability from nth state to mth state is given by the formula A m1 of t square is equal to 4 sin square omega ml t by 2 whole divided by h cross square omega square ml into square of the matrix element. This is the probability of transition from one defined nth state to single mth state. If you want to calculate the transition probability from the defined nth state to any one of the state existing in the continuum, just you have to take over the summation to the left hand side. So summation of this quantity is equal to integral of square of the am1 of t into rho m into d, because in between E and E plus d, rho m into d states are present. So substitute the value of am1 of t square, then the equation 2 is modified in this form. Now take this 4 sine square 4 into square of the matrix element rho m divided by h cross square outside. Inside the integral sine square omega ml t by 2 divided by omega square term is present, that should be multiplied by dE. You know that d equal to h cross omega. Therefore, d equal to h cross into d omega. Substitute all these things in this equation. Now we can get the equation of form 3. Here, instead of d, we have to put h cross d omega. Here h cross square is present, so finally we can get 4 into square of the matrix element divided by h cross, then rho of m sine square omega ml t by 2 divided by omega square ml into d omega. Put x equal to omega ml into t by 2. Then omega ml is equal to 2x by t. D omega equal to 2 by t into dx. Substitute all these values. And omega square is equal to 4x square by t square. Substitute all these values in equation 3. Now equation 3 becomes t equal to 4 into square of the matrix element divided by h cross rho of m sin square x divided by 4x square by t square. Instead of d omega, you have to put 2 by t into dx. If you simplify, we can get this equation. Square of the matrix element divided by h cross rho of m 2t, then integral limit varying from minus infinity to plus infinity sin square x by x square into dx. This is the standard integral. The value of this integral is pi. So the transition probability t equal to 2 pi by h cross, then absolute square of the matrix element rho of m into t. Now the transition probability per unit time is, without t we have to write the above relation, 2 pi by h cross h1 of ml square rho of m. This is called the Fermi Golden rule. The theory of scattering can be explained with the help of this Fermi Golden rule. The transition probability per unit time is non-zero only between the continuum states of the same energy. If the transformation is taken place from one eigenstate to the continuum of state, the probability of transition is non-zero, otherwise the probability is zero. Then the probability per unit time is proportional to square of the matrix element and density of the final state, it is rho of m. This is a simple definition for density of states. The density of states is defined as the eigenstates available to occupy in the given energy region. That's all about the Fermi Golden rule.